Next up, we have Ethan Shavers, who's with the U.S. Geological Survey, actually works in CGIS, which you've heard much about by now. He'll be talking about exploring and mapping LiDAR point clouds.
Great, thanks, Sam. Thanks, everybody. I'm going to talk about a tool we're developing that we hope some of you may find useful, or at least interesting. I'll describe some of the motivation and the background for the tool, and then update you on the development, as it's not done even given past deadlines. The USGS National Surface Water Map data is the National Hydrography Data Set. It's been shown by others that the largest discrepancies in the NHD are among the small headwater streams. This map shows the percentage of 1 to 24K first order features in the NHD. Nationally, they make up greater than 50% of the NHD by length, and we believe this to be an underestimation. The takeaway from this image is that the majority of the features in the NHD are small headwater streams, and as I said, the largest discrepancies in the NHD are among the small streams. So small headwater features are a large part of the NHD and undermapped. They're also highly subject to change. A single extreme weather event or subtle change in hydrologic conditions could change the course or permanence of a feature, such as the one shown here. Tools for identifying stream position and extent are thus important for maintaining an accurate NHD. To date, automated tools are generally limited to types of flow modeling, yet determining stream extent and permanence are not resolved with those tools. Well, anyway. This is not, okay. Sorry, it's an older slide set. I'm going to skip through some of these for the sake of time. So there are scenarios where we do have some options for understanding stream extent and permanence. For instance, with satellite data like this nice Maxar data, which is collected quite often, and we can see streams in the open and arid regions quite easily. This image is from South Dakota, but as we know, much of the world is not arid, and most stream corridors are bounded by vegetation, which confounds most optical reflectance remote sensing solutions. We've been thinking about this issue for a while. I think we began first looking at some sort of corridor analysis while investigating LiDAR return point density as a potential useful metric for hydro mapping work. Early on, we saw trends in above ground return point density patterns that correlate with surface water occurrence. As you can see here, this is one of our study areas in North Carolina. The Piedmont region is actually very forested. I cut out the slide with the imagery, but we have field validated stream head data here seen as in the red dots. The lighter areas are where there is more dense above ground vegetation, low brushy vegetation, in a region with mostly forested cover. And the trend is following what we know to be the channel network below the field validated stream heads. Here we see the validated perennial and intermittent streams as checked lines, well aligning with the low vegetation pattern. So we're seeing this with the rudimentary filtering of the point cloud in one region, but what other patterns might be there in the above ground structures of the canopy occluded stream corridors? This is data we have been looking at for deep learning inputs, but we'd like to dig in and get a better look at just, zoom in and look at those corridor areas of the LiDAR data. Some preliminary work has been done to test characterizing point cloud corridor attributes, but it was an involved workflow and not easily tunable, although what we found was encouraging. For example, we see increases in the lowest and highest tier point density as we move down a channel for intermittent and perennial streams. An example of this is in the bottom right plot, where aggregated tiers along a cross section, the density is aggregated and plotted in 10-foot height increments. But what we would like is a more granular view, such as in the top right plot, where we can see return densities for a single cross section in a plane perpendicular to the channel line. showing higher point density in the upper canopy as we would expect. This is the type of information we'd like to get from the output of our tool. In 2020, we learned about the water rat project that was doing pretty much what we wanted to do, only with water quality and bathymetry point data. In the bottom three plots, the tool is generating cross-section statistics and interpolations, similar to what we've been trying to do, as well as interactive visualization of the data. This was a Community for Data Integration, or a CDI project, funded project. Finally, in 2021, we found a way to collaborate with the developers of WaterRat. We submitted a proposal to fund our CoreViz development. And here, when we say corridor, it refers to regions of a LiDAR point cloud around linear features like shorelines, roads, and power lines. These corridors are regions of importance to all kinds of research and decision-making, be it ecology, geology, or urban planning. LiDAR data attributes like return point density and intensity carry enormous potential to inform such research and mapping. High spatial resolution LiDAR data is being collected for the conterminous United States, and we want to open it up to more users. There are several open source tools out there that do visualization of point cloud data, yet they require some domain and computer skills that may be a barrier. And we hope this tool will be an easy way that people can take advantage of all this great data. So like I said, we had a project funded by CDI in 2022 to support the building of this tool. So CDI is a USGS group that funds small projects that work on like data accessibility and other fair data practices. Our requirements or the basic goals for the build are that minimal inputs will be a line and a shape file, line shape file, and last point file. Last is the data file type that USGS and many others use. We want to be able to visualize the data, but most importantly for us is the automated output of linear point statistics along with relative metadata in a standardized, repeatable way. That's the main goal for us. We're still in development phase of CoreViz, but this is a working format of what we're using for the output statistic data. There will be a row for every cross section and a unique ID you see in the first column. Within each row, the center position and coordinates of the samples along the cross section are in the second column, and the elevation at each of those points and the vertical intervals of the matrix are in columns 3 and 4, so that every cell in the following statistic matrices can be oriented in 3 dimensions. And then, as I mentioned, there are the stats matrices, and those are not exactly the stats. We know that's the type of thing we'll have as outputs. Here's a recording. Yeah, looks like it's playing. Of the state of the build as of last week. We see the input lines on the bottom right in an OpenStreetMap viewer with our location as a red dot. Navigation in the main viewer is done with the mouse to look around, and then with the arrow keys to actually move. You can go up and down, forward and backwards. And you can see the cross section in the lower panel of the position that you're currently in. And there's still some bugs we got to work out with orientation. The arrow is that north arrow is actually east-west is reversed in this. We fixed that since then, though. And you see on the right where you load your shape files and last files, and there's also an output for the modified lines. As we have it now, when you input a line set, it automatically does a splining and resampling so that there's a standardized, evenly spaced vertices for sampling across. And so we want to be able to save the files that are created there. So moving forward, we still need to work on including some options for statistics output, including the download. The minimum will simply be a file downloader similar to the line download option in the video. More specific options regarding feature selection and point filtering are on our wish list, but may not be included before we do the first release. We'd also like to see clustering and surface rendering too in future iterations of the tool. Still left to do before we do even our initial release is figuring out what our metadata is going to look like. These are some OGC attributes for line features and linear observations. On the right is the observations, and that's actually time series observations. So I'm kind of using it as a guide. I'm not exactly sure how best to do that data, but this is what the type of thing we're looking at for developing the metadata. Yeah, and we plan to release the tool as a downloadable executable open source tool, and we'll hope to publish some results of our output statistical analysis. That's all I have.
Ethan, do we have any questions? So I have a question.
Yeah.
When you say, it's just a technical question, so any kind of a line file will you be thinking of other ways to take in the shape file other than a shape file? Other vector input formats?
Oh, sure.
Okay.
JSON type of thing.
Right.
Yeah, I mean, that's doable, definitely. Right now, it's
Something
just
to
a
think
shape
about.
file.
Right.
There's lots of things.
I mean, I know we're in Esri and the shape file's good, but.
Right now, it's a good point.
Great.
It's things we're thinking about. You know, they only give you so much money and they expect you to spend it in a year with CDI. It's more like
Right.
a seed grant thing. So we're trying to cram through as much as we can to get those stats.
Great.
Most important thing.
Other questions? All right. Well, thank you very much,
Thanks.
Ethan.